important to be able to recognize isomers because they can have different chemical, physical and biological properties. So, today we are going to discuss stereo or space isomerism, as space isomerism is of two types, optical isomerism and geometrical isomerism. Today we will be discussing geometrical isomerism. Our main focus will be on geometrical isomerism in 4 coordinated complexes and 6 coordinated complexes. Before proceeding further, let us recall what we have discussed in last lecture. In last lecture, we talked about writing formula of coordination complexes, isomerism, different types of structural isomerism, that is linkage isomerism, coordination isomerism, ionization isomerism, solvate or hydrate isomerism and polymerization isomerism. So, let us recall what are isomers. Isomers are two or more compounds that have the same chemical formula, but a different arrangement of atoms. Two principal types of isomerisms are known among coordination compounds: structural isomerism and stereoisomerism, which is also known as spatial isomerism, each of which can be further subdivided. Here you can see isomerism can be subdivided in two parts, structural isomerism and stereoisomerism. Different types of structural isomerism we have discussed in last lecture. Today we will be discussing a type of stereoisomerism, that is geometrical isomerism. So, what are stereo or space isomers? These isomers differ only in the spatial arrangement of atoms or groups about the central metal atom. It is possible only in the complexes having coordination number 4 or greater than 4. The two types of stereoisomerisms are geometrical isomerism and optical isomerism. Geometrical isomers are isomers that differ in arrangement of ligands around the metal or the central atom. In other words, these isomers differ from each other based on where the ligands are placed in coordination compound. There are two main types of geometrical isomers: mer-fac isomer, or you can say meridional facial isomers, and SIS Trans Isomers. Let us first discuss SIS Trans Isomers. SIS Trans Isomers are isomers that differ in the arrangement of two ligands in square planar and octahedral geometry. Cis isomers are isomers where the two ligands are 90 degrees apart from one another in relation to the central atom. This is because cis isomers have a bond angle of 90 degrees between two same atoms. But the trans isomers, on the other hand, are isomers where the two ligands are on opposite sides of the molecule, because the trans isomers have a bond angle of 180 degrees between the two same atoms. When naming cis or trans isomers, the name beginning either with cis or trans, whichever applies, followed by the hyphen, and then the name of the molecule is written. For example, a cis isomer of COCl2F2 would be called cis COCl2F2. There are two symmetrical geometries of complexes of 4 ligands, tetrahedral and square planar. Let us discuss geometrical isomerism for tetrahedral geometry. The tetrahedral complex Ma2B2 has no geometric isomers. As this figure shows, a tetrahedral geometry for Ma2B2 allows only one arrangement of the ligands. The group on the top can be rotated to look like the group on the bottom. A and B are any two ligands. In this case, all the 4 ligands are symmetrically arranged with respect to one another. hence geometrical isomerism is not possible. The square planar geometry for MA2B2 however gives two possible arrangements, cis and trans isomers. For example, here is cis isomer for COCl2F2. You can see this pink color is the atom of cobalt, blue are fluorines and green 2 chlorines. In this figure, 2 chlorines have a 90-degree angle and 2 fluorines also have a 90-degree angle. Hence, this isomer is a cis isomer. In this figure, you can see that the bond angle between the similar atoms is 180 degree. Hence, this is the trans isomer of COCl2F2. Hence, it can be named as trans dichlorido fluorido cobalt 4. Now, we will discuss the geometrical isomers of square planar complex diamine dichlorido platinum 2. The two arrangements for PTNH3 whole twice Cl2, that is cis and trans diamine dichlorido platinum 2 are shown here. The first one is cis because the bond angles between two similar atoms are 90 degrees. In second one, the bond angles between two similar atoms are 180 degrees. Hence, this is trans isomer. The existence of two isomers of PTNH3 whole twice Cl2 is evidence of a square planar geometry because the tetrahedral geometry would not give the isomers. The cis isomer has been used successfully in cancer chemotherapy. The trans isomer has no such activity. A square planar complex of the type MABCD shows geometrical isomerism where cis and trans positions of two groups relative to each other are taken into consideration. In the cis isomer, the two groups are next to each other, that is at 90 degrees in relation to the central metal ion, whereas in the trans isomer they are opposite to each other, that is at 180 degrees relative to the central metal ion. MABCD shows 3 isomers, 2 cis and 1 trans. If we consider these isomers with respect to A and B, you can see in this form A and B are cis, in this form also A and B are at cis positions, but in this form A and B are at trans positions. So, with respect to A and B ligands, this form is cis, this one is also cis, but this one is trans form. But if we consider the two ligands A and D, you can see in this form A and D are at cis positions, here A and D are at trans positions, and in this one A and D are at cis positions. So, with respect to the ligands A and D, this form is cis, this one is trans, and again this one is cis. Hence, 2 cis and 1 trans form. Now, let us discuss the complexes of coordination number 6, that is octahedral geometry. Cis trans isomerism can also occur in octahedral geometry. In this figure, octahedral geometry has been shown. Here is metal and the 6 positions of octahedral geometry are numbered as 1, 2, 3, 4, 5 and 6. Now, cis positions are 1 and 2, 1, 3, 1, 4, 1, 5, 2, 3, 3, 4, 4, 5, 2, 5, 2, 6, 3, 6, 4, 6 and 5, 6, and the transpositions are 1, 6, 2, 4 and 3, 5. Now, let us discuss a cis isomer of the type Ma2B4. Here is the example of cis SCl2F4. This isomer is cis isomer because both the chlorine ligands are on the same side and the bond angle between the chlorine atoms appears to be 90 degrees. Here is the trans isomer for SCl2F4. This isomer is a trans isomer because the chlorine ligands are on the opposite sides and the bond angle between the chlorine atoms is 180 degrees. All other isomers are essentially just rotations of these two isomers. Remember that when trying to find cis and trans isomers, look at the arrangements of the ligands. If two same ligands are on the same side, it is a cis isomer, and if the two same ligands are on the opposite sides, it is a trans isomer. Another way to tell the isomers is the bond angles. Cis isomers have a 90 degree bond angle, whereas trans isomers have a 180 degree bond angle. Now, geometric isomers of tetraamine dichlorido cobalt 3 ion. Here you can see the two chlorines are at 180 degrees to each other. So, this is a trans isomer. The complexes involving bidentate ligands such as ethylene diamine can also exhibit this kind of isomerism. You can see in this figure. This is cis isomer as the bond angle between two similar chlorine atoms is 90 degree. But in this form, as the bond angle between two similar chlorine atoms is 180 degrees, hence this is trans isomer. The two ethylene diamine ligands are shown in this way. Complexes of the type Ma2, B2, C2 can exist in several isomeric forms. Consider as an example Cr H2O whole twice, NH3 whole twice, Br2. In first form A, the members of all the three pairs of like ligands are trans to each other. Hence, it is named as trans diamine, trans diaqua, trans dibromido chromium 3 ion. And in the second form, the members of all the three pairs of like ligands are cis to each other. Hence, this form is named as cis diamine, cis diaqua, cis dibromido chromium 3 ion. In third form C, the members of one of the pairs may be trans to each other, but the members of the other two pairs are cis. Hence, this will be named as cis diamine, trans diaqua, cis dibromido chromium 3 ion. In fourth form, that is in D, only one pair of ligands are at transposition. This ligand amine is at transposition. These two ligands are at cis positions to each other. Hence, this complex will be named as trans diamine, cis diaqua, cis dibromido chromium 3 ion. In fifth isomer, only two bromido ligands are at trans. These two ligands are at trans positions. these two are at cis and two aqua ligands are also at cis positions. Hence, it will be named as cis diamine cis diaqua trans dibromido chromium 3 ion. Octahedral complexes with the general formula Ma3B3 can exhibit another type of geometrical isomerism called meridional facial isomerism or MER-FAC isomerism. Meridional facial isomers are easier to notice than SIS trans isomers in the sense that they only exist in octahedral geometry. Just like SIS trans isomers, meridional and facial isomers are determined based on whether or not the ligands exists on the same site. Instead of dealing with two ligands, meridional facial isomers deal with three ligands. If the three ligands are all on the same site, the isomer is called a facial isomer. Another way to identify facial isomers is to look at the bond angle between the ligands because facial isomers have a 90-degree bond angle between each of the three atoms. The meridional isomer, on the other hand, is where only two of the three ligands are on the same site. In meridional isomers, there exists a 90-degree, 90-degree, 180-degree bond angle between the three same ligands. It can also be said that if three donor atoms of the same ligand occupy adjacent positions at the corners of the octahedral face, we have the facial isomer. When the positions are around the meridian of the octahedron, we get a meridional isomer. In terms of nomenclature, MER-FAC isomers follow the same rule as a SIS trans isomers, where you put the isomer type followed by a hyphen followed by the molecular formula. For example, as this isomer is facial isomer, hence it will be named as FAC COCl3F3. You can also see this isomer in two-dimensional version. It is easier to see how the ligands are all on the same site. In the three-dimensional version, one can observe that the bond angle between the three same ligands is 90 degree, thus making the isomer as a FAC isomer. Here you can see that three similar ligands are on the meridian of the octahedron, hence this is known as meridional isomer and it will be named as MER COCl3F3. Here is a stereo view of facial triamine trichlorido platinum 4 ion. The three chlorido ligands are all on the one triangular face of the octahedron and the three amine ligands are all on the opposite triangular face. In the other isomer, the three similar ligands lie on the same plane. This is called meridional isomer. It is so called because the plane is analogous to meridian on a globe. Here is a stereo view of facial triamine trichlorido platinum 4 ion. The three chlorido ligands are all on one meridian, that is in one plane, and the three amine ligands are all on a perpendicular plane. Hence, this isomer is a meridional isomer. Now, let us discuss some problems to understand the geometrical isomerism in coordination compounds. Here is the first problem. Draw all possible geometrical isomers for the tetrahedral molecule MnCl2F2. Now, you must remember that tetrahedral molecules do not have geometrical isomers. Hence, MnCl2F2 has no geometrical isomers because tetrahedral molecules do not have geometrical isomers. There is another problem. What type of isomer is the molecule pictured here? Are there any other type of isomers possible for this molecule? The molecule FeBr2I2 pictured in this problem is a cis isomer or cis FeBr2I2 because both the bromines and iodine ligands are on the same side. There is one more stereoisomer for this molecule, which is trans FeBr2I2. This isomer is trans isomer because the two similar ligands, bromines, are on opposite sides and two similar ligands, iodine, are also on opposite sides. Let us discuss one more problem to understand the geometrical isomerism in octahedral complexes with bidentate ligands. How many geometrical isomers are possible in the following coordination entities? Cr C2O4 whole thrice 3 minus and CONH3 whole thrice Cl3. For Cr C2O4 3 minus, no geometric isomer is possible as it is a symmetrical bidentate ligand. For CONH3 whole thrice Cl3, two geometrical isomers are possible. One is facial as the three similar ligands are at the three corners of a face, and the other is meridional as the three similar ligands are at the same plane, that is at a meridian of the octahedron. So, this was all about geometrical isomerism in coordination compounds.